So what we will do today is that we will talk about strengthening mechanisms. So if you remember in the last two lectures, we talked about dislocations or line defects in crystalline materials. And today we will learn how we can use different types of strengthening mechanisms to change the mechanical properties of the materials. And again, everything is related to behavior of dislocations. We will also start a discussion about surface properties of the materials. So we will finish the discussion about line defects, and we will continue in 2 dimensions. So we will talk about specifically surface energies and how to calculate the equilibrium shape of a crystal when it grows in a nanocrystalline form, or when you form a polycrystalline material, what will be the equilibrium shape, etc. So we will continue this discussion about surfaces, specifically about surface defects on Friday. And with this, we will complete the discussion about 2-dimensional features in the materials. So if you remember, last time we talked about the fact that we introduced dislocations as a concept in the materials to explain discrepancy between calculated and measured critical stresses that are required to deform material. And we also mentioned that the mechanical properties, specifically the strength, strongly depend on the way and the probability that the dislocations will be formed within the material and that they will slip or that they will move throughout the material itself. So we already last time mentioned that the mechanical resistance or the strength of the material is directly related to the ease of generating and moving dislocations. So today we will talk about different types of strengthening mechanisms. So these are the mechanisms or types of processing procedures that you can introduce into the material to strengthen the material. And when we say strengthen, what that means is that you can increase the stress, or you can increase the critical value of the stress or the force that you need to apply to a material to either plastically deform it or completely disassemble, right? So to either break it or plastically deform it. So the question is, what do you need to do with the material to increase that force that is required for these two processes to happen? So we will specifically talk about 4 different processes. So the first one will be grain size and shape engineering. What that means is that by changing the shape and the size of the crystals in polycrystalline materials, we will be able to increase the strength of the material. The second will be solid solutions. By introducing different types of atoms in a crystal that have either larger or smaller atomic radii, the material will be strengthened. The third is forming precipitates. In a certain sense, you can think this is an extreme case of solid solution, but actually the precipitates and the formation of the precipitates and the type of the precipitates very often is different from the solid solutions, but it can be thought as the extension of this. And fourth is so-called cold work. And as we will see, the cold work refers to the process by which you deform the material multiple times. So you first deform it, and then the strength of the material increases throughout this process. So you first mechanically deform it until you reach the point where this process is actually relatively difficult. So we'll learn about what is actually happening during this process. So let's start with the grain size and shape engineering. First of all, the grain, when you have a polycrystalline material, and if you compare it with a single crystalline contrapart, polycrystalline materials in general will be much stronger. They will have higher strength. The reason for that is that they will be composed of different grains. So this is illustrated here. So you have one grain where the atom planes are in one direction. They're perfectly arranged. And then there is the neighboring grain indicated as a grain B. Again, the same crystalline structure, the same types of planes, but there is misorientation between these planes. So in the first case, for example, the planes run in this direction. In the case of the grain B, they run at a certain angle. So depending on this misorientation between these grains, these grain boundaries or the interfaces, so this would be called a grain boundary. So these can be either low or high angle grain boundaries. But the reason why polycrystalline material is stronger than a single crystalline material is because of the fact that if you want to plastically deform a material, the process, how it happens, involves slip of the dislocations. So you have one particular dislocation in grain A, And when you apply a stress onto the material, the dislocation will move, let's say in this direction. And when it reaches the interface or the grain boundary, the interface between grain A and B, in order for this dislocation to propagate, it would need to change the direction. So this would be the identical plane in the neighboring grain. So there is some kind of a barrier for the dislocation to go from grain A to grain B. Effectively, what that means is that the dislocation will be trapped at this grain boundary. So if this grain boundary is highly mismatched, if this is a high angle grain boundary, then this trapping of the dislocations will be more likely than if this was a low angle grain boundary. So in order to improve the material strength or increase the strength, you can increase the angle of the misorientation, or you can reduce the size of the grains. So the size of the grains simply means that you will have more and more grain boundaries, meaning that this individual grain, dislocation itself will move just by a little bit, and then it will reach the grain boundary. So if you think about the grain boundary engineering, so you can either change or influence the angle or the size of the grain boundaries. So if this is a typical polycrystalline material, so these would be individual grains, right? So these are individual grains, and the lines in between them are grain boundaries. And the lines within individual grains will be slip lines. If you remember last time I mentioned, if you have a crystalline material and if you apply force or stress into the material will slip, and you will, on the surface of the material, you will have these slip bands. And in this particular case, in each of these grains, you will have these individual slip bands. And they simply indicate what is the orientation of the slip system in particular grain. So we can ask a question: if you have a polycrystalline material, and if you apply a stress in a certain direction, which of these grains will slip first? Or in other words, which of the grains will fail as the first one? So what would be your answer if I asked you that question? So each grain has different orientation. We're applying a stress in certain direction, and I'm asking which one is more likely to fail than the other. Yes?
Use product of cosine lambda and cosine phi to be the smallest.
Exactly. So the answer was wherever is the cosine lambda and cosine phi maximized. So we last time learned about the Schmidt's law, which told us that the resolved shear stress in a particular slip system, which is the set of planes in the material, is equal to the applied stress times cosine lambda times cosine phi. And I won't go back into the definition of these angles, but they define the angle between the normal of the plane and the direction of the stress, as well as the direction of the resolved force and the stress direction. And this TR will be maximum for lambda equals phi equals 45 degrees. In other words, the grain that satisfies these requirements will fail the first. So you can then ask a question: can you engineer a material that is already polycrystalline in a way that you can either minimize or maximize this depending on the application that you want, right? So, and this can be done using so-called rolling processing. So if this is a typical polycrystalline material, the orientation of the grains and the size of the grains follows. So the orientation is random, the size of the grains depends on the processing parameters. But if you start with a given material, you can roll the material. So you can apply rolling techniques to somehow elongate the grains and change their relative orientations within the grain itself. So starting from isotropic case, where the orientation of the grains is random, you come into the situation where this is not random anymore, so it's anisotropic case. So this type of strengthening processing and strengthening mechanisms using grain engineering is very, very common. So in material science of metals and other materials, this is very, very common. Okay? So the other strengthening mechanism that we mentioned is solid solution. So if you remember, the solid solution simply means that you're introducing foreign atoms into the material itself. And the reason why particular material that has solid atoms will be strengthened is because, again, if you have a dislocation that propagates throughout the material, if this was a perfect crystal, this dislocation would simply move if you apply a stress. However, if you have an atom that is smaller or larger than the atoms of the host crystal, there will be a local strain around that particular solid atom, meaning that the planes, instead of having perfect position, in this particular case horizontal, they will be bent, so there will be strain. So this dislocation, there will be again a barrier for the dislocation to propagate. Okay? So just to illustrate that this is indeed the case, that things do work, this will be the tensile strength as a function of the concentration of nickel, and this is in the case of copper. So you take copper and you start introducing nickel, and the tensile strength in pure copper has a certain value, roughly 210 megapascals. And then when you introduce and increase the concentration of the nickel atoms, this goes up. Okay? So these are actual measurements, and this is something that can be observed directly. So again, very commonly used, as in the case of the grain boundary engineering.